to do some yeah, definitely some finite element analysis. What we can do in this finite element method is like we will be modeling this specimen whatever is under this tension, and we can design the whole experiment in finite element analysis. We will be using abacus here for doing our finite element analysis. To we will first model it and then meshing it, and then give us the load what we want to give to this material and how it has been failure. Everything we can generate through it, and we can make the videos also, the same experiment video, and we get a lot of data, useful data. And the thing is that how good I am in this finite element method can be known from the model whatever I am preparing there, because this model preparation and this experimental value, both things should be matching ideally. So I'll be trying my best to do this analysis, and I'll try to do this analysis properly. And what I can say, I'll be presenting all those things in my thesis. So next, okay, so besides all this torsion testing and failure of the material, experimental work, and this microscopy, and also I want to add that if I get sufficient time, I want to do this transmission electron microscopy also for studying these dislocations, because in many books I have read about this dislocation movement being studied by this TEM. So but there's a little bit of problem, because it will take a huge time to making the samples and cleaning it and putting in the TEM and studying it. So I'll try my best to do that part also in my project. So next, besides all this, I want to model a miniature of this experiment through studying this molecular dynamics and using these lamps. So this torsional behavior of studying this for BCC material has been done in our institute also, for BCC steel, I can say. So now basically this titanium modified steel has a lot of component inside it. It will be like chromium, manganese, molybdenum, nickel. Because this is a austenitic, the structure will be FCC. Because this is stainless steel, it will be like the chromium and nickel will be there. So lots of materials will be involved here. But because this is steel, the most of the part will be steel, and if we want to include carbon, we can include carbon also. I'll try that later, but right now I want to study the torsional failure for around 20,000 atoms of FCC, and study this failure using these embedded atom potentials. So in this process of studying this material in a very molecular or atomic scale, I learned molecular dynamics, and then I learned lamps for doing all these things. So in lamps, what we can say, this embedded atom potential for Fe bonding is already available, and with Fe there are some other materials are also available. I have seen in this, I checked in this internet, so some more potentials are also available, and the best chosen potential for studying alloy is this embedded atom potential, what you know. So there are other few metals which will be involved in this process, but we want to avoid it for right now. So right now, as I mentioned, I will be doing it for 20,000 atoms, and I will be putting all these things in my thesis also. And as much as I can do, finishing this work, because here the facilities are already available, these clusters and this workstation from Windows, both are available. So I will try to do my best and do a lot of modeling as much as possible. So in steel, this carbon is another component. That's why we call this iron steel. So this carbon amount will be around up to 2%. So in this austenitic stainless steel, it is a medium carbon steel, so it will be like 0.02 to 0.04%. So we, from my perspective, I want to involve this this carbon also in my lamps designing. So initially I will be doing it for 20,000 atoms, and the same thing for some time step or And generally I'll be doing this modeling for ferrous bonding only. And next, this computational physics by Thiessen is very much helpful for this purpose, and LAMPS tutorial definitely it's the only thing I have to study this computational study for this molecular dynamics. But later I will try to simulate this movement of the grain boundaries through lamps also. That's going to be very much difficult and it will be much more complex, and I'll try to do it as much as possible in this computational facility here in Indira Gandhi Center for Atomic Research. So besides all these, there are many toolbox available in MATLAB which can help simulating the microstructure. So there are many available modules out there which can help us understanding the microstructure. So in this test environment, like this phase field model is one of them, and this XFM is extended finite element method is also there. So these things can help studying the microstructure, and if possible I will be studying this. There are already papers are available where they are studying this microstructure simulation through Monte Carlo method and other methods. So I'll be trying to include all those studies here also, and if possible for me, and I'm trying my best to do all this work to extend my work. Like as I told you that this lamps I will be doing it a failure of a BCC of a FCC material, because Australian stainless steel is FCC under 20,000 atoms. But if possible I will extend this work to the grain boundaries also. And besides this, I am also involved with Professor Shishir Roy in Indian Statistical Institute, Kolkata, India. So there I am planning to finish some work by December. So this work will be like studying the tunneling tunneling for multiple barrier in graphene. So in graphene, later in my PhD also I'm willing to work on graphene more than this material thing. But I'm open to both the things, but generally my interest is in graphene is quite strong. What I can say, this graphene or carbon nanotube or anything, this graphite or multilayer graphenes or anything I want to study in my PhD. So mostly this electronics, in this world of electronics, this silicon is like it's come to end of its life. We can't increase the number of transistor in a area that we all know about that thing. So currently we want to do this. We are trying to use this graphene as studying this electronic property. So there are a lot of work is going on, as everybody know all these things. So I'm just mentioning. So in this graphene, graphene is a wonder material after its discovery from 2004 by Andre Gleeman, Novoselov. It has become one of the most studied material in what you can say in physics, in chemistry, or in material science, or many things. In metallurgy also there are carbon reinforcement is there. So there are a lot of things what people are studying now. So graphene, in a word I can say that it gives us a chance to study the novel quantum phenomena in a low dimension, which may help in inventing novel electronic devices. So in this work, what we will be doing is, like, first of all, it will involve the study of like the university level quantum physics, what I actually didn't get in my coursework, but upon my interest, as I'm interested to make my career in physics, I want to study. So I contacted this professor in Professor C.C. Roy in ISI Kolkata. So he helped me a lot studying this and understanding this quantum physics. In last December also we sat for many discussions, and this time also I will try to finish. I will be visiting there so that I can finish that work. So university level physics, and particular to this thesis, before doing any calculation on the graphene, there will be study of quantum tunneling for different barrier. So okay, I can sequentially tell what I want to do in this project, actually, in this tunneling time for multiple barriers in graphene. So it will be like as we My work will be involving like the study of tunneling for different barrier geometry. Then tunneling of carrier through a barrier is characterized not only by transmission and reflection probability but also by its time. But like it will involve a lot of study about this university level quantum physics. So if we take any book of quantum physics, this transmission probability and reflectivity is always discussed in any book, but this actual time what it takes to tunnel a barrier is always a discussions in these journals and letters like that. So Professor Sishiroy and his student is working on this tunneling time for quite some time now. So his students they have worked. If I say technically what I am going to present in this work in ISI Calcutta. So that is like first of all it will be involving I will write about and I will put my study about this quantum tunneling transmissibility for different geometrical barriers, and the next it will be like the studying about the this graphene tight binding model and other novel quantum phenomena whatever is still not invented through graphene. And next it will be like this novel quantum phenomena will involve a lot of study about this massless Dirac fermions, quantum Hall effect, lattice distortion, edge state in a strong magnetic field, and other fractional quantum Hall effect. As you know, this fractional quantum Hall effect can be a key to this developing this quantum computer, and might be graphene can be one of the materials there. Nobody knows till now. So then studying about this claim tunneling,